I would like to take the opportunity to advertise our products of the combination service for time-varying gravity fields. COST-G is a product center of the International Gravity Field Service of the AG. It was inaugurated in 2019, so it's a bit younger than the IGS, but I hope to all welcome you to our 30th anniversary in 25 years, hopefully also back in Bern. The idea is quite simple. We have monthly gravity field solutions from different analysis centers, and we do a combination. So we will find many similarities to the IGS. Of course, by this combination, no new information is introduced into the combined product. So the effect that we see here is a reduction of the analysis noise of the different solutions. Our products are the monthly combined gravity fields based on data of the GRACE follow-on missions. So GRACE 2002 to 2017, there we have combination of reprocessed data, and for GRACE follow-on 2018 till now, it's an operational combination. And our main products are these gravity fields in spherical harmonic coefficients, but many of our users come from the geophysical community, and for those we also provide grids of water storage. That's more useful for them. They're not so much used to these spherical harmonic coefficients. And what is the main signal contained in these products? You all know about the mass loss, for example, in polar regions. Here you have an example of Greenland. You have in the linear plot, you see the trend over many years and the annual variation. And these are the main type of signals that we see in our monthly gravity fields. So these lines are computed from our monthly gravity fields. So it's interesting for the glaciologists, for the hydrologists, or all people interested in climate research. Why may it be interesting for you? Well, we have the direct impact of mass on satellite orbits via gravity. And well, we also have another effect. So we have a loading effect by the mass that is represented by the monthly gravity fields. I'm not aware of any studies using our products to predict station movement, but maybe I'm only in the wrong conferences. Maybe you know more than I do. And I must admit, our monthly gravity field combinations, they have a latency of about 3 months. So they are not useful for this operational orbit determination that many of you are doing. And so to help for orbit determination, we also provide a fitted signal model fitted to the monthly solutions. I must admit, we are not the only ones with this idea. So there exist gravity fields, including time variations fitted to monthly models. For example, these IGS models. And here I show fits to mass variations in river basins. And the black dots are the monthly evaluations of our monthly combined gravity fields. And in light blue, you see the evaluation of the IGS series of 4, including data of the GRACE mission till the end of 2017. And you see, after a few years, the prediction computed from this model can be quite off. Now we have a new model, IGS release 05, including data till 2022, and it still fits very well. But also this model will get older. And now the idea behind our COST-G model is to have a model that is updated regularly. Every 3 months we will include the newest data from GRACE follow-on, as long as we have GRACE follow-on. So the red curve that represents the fit of our model will not get old, as long as we have GRACE follow-on, or maybe in the future GRACE C or Magic. So we hope that the story will continue. But for reprocessing, well, they are not comparable in quality to the long-term IGS model. So it's only for the new POD or POD of any satellites, I hope. I have to point out one problem. You may have heard that one of the main components of the gravity field C20 is not well determined from trace or trace follow-on. So you here see the long-term time series of C20 values derived from satellite laser ranging, and for the last 5 years, values derived from trace follow-on. They are not comparable. And believe me, the black line is better than the colored lines from trace follow-on. So to provide you the best possible information, we replaced this C20 coefficient in our combined models in the fitted signal model by values derived from SLR and satellite laser ranging. Now let's do some validation. Let's first look at some low-flying satellites. Christoph Förster used our model for some low-flying satellites and compared the orbit fit of the monthly solutions and the fitted signal model. And for 11 out of 12 test months, he saw an improvement of the fitted signal model compared to the monthly models. We are a bit surprised because we believe that in the monthly models there's the best signal content that you can achieve. But obviously the low-flying satellites are also sensitive to the higher degrees of the gravity field, and there the fitted signal model shows a noise reduction because of the fit compared to the monthly ones, and obviously low-flying satellites profit from this noise reduction. And so the fitted signal model is even better than the monthly solutions. Not shown are static gravity fields. They are much worse, but I didn't include them here to show too many numbers. So for LEOs, use our model, you will benefit in the LEO POD. Does it also help for the high-flying satellites? So we know GNSS are at a much higher altitude. So Emilio did a comparison of orbit fits also for high-flying satellites, used the standard parameterization processing, used a decoder analysis center, and computed 3-day arcs on the one-hand side based on the reference gravity field EGM 2008, also including drifts for the very low zonal harmonics C20, 30, and 40. And then for comparison, orbits derived from the COST-G fitted signal model, we computed orbits for 4 years, 2018 to 22, so quite a lot of data. Here are shown orbit overlaps, midnight disclosures, based on the reference gravity field, and its computation of 3-day orbits, and always the middle day was taken for to compute this midnight disclosures. And in the legend you see the RMS of the differences. Now I switch forward using the COST-G model, and if you don't see any difference, don't be surprised. There is no real difference. In the orbit positions, we do not see a benefit of using these fitted signal models from COST-G. Obviously, the orbit positions are not really sensitive. The GNSS satellites are just flying too high. And the SNR validation shows the same. That's the same story. It doesn't really matter for the orbit positions which model you introduce. EGM 2008 in this case, or just COST-G model. But I was told that you are not only interested in the orbits, but also in geophysical parameters. For example, in the length of day. You co-estimate length of day together with the orbits. And here I show a comparison of length of day estimates compared to the consolidated CO4 time series of the IGS. And once computed based on the reference times EGM model, one on the COST-G model in red. And you see there is a difference in the a systematic difference in the residuals in the left plot. And if you take a spectral analysis of the residuals, then you find out that the difference is mainly on the annual frequency. And there you see a significant reduction of differences. So the length of day estimates significantly profit when we include this meaningful variation, time variable gravity field variation from the COST-G model. So I hope that this will convince you to test out the COST-G model even for the orbit determination of the high-flying GNSS satellites. At CODE, we already use it. And it's updated every 3 months, so it involves some work to be always up to date, but I think it's worthwhile. Where to get it? So the gravity fields are available from another IAG service, the International Center for Global Earth Models, and there you have to go to the time variable models, and you will find the section on for COST-G here at the bottom, and there this FSM is a fitted signal model. You can download the models there, and every 3 months they will be updated. Sometimes it's late. We have 1 more month of latency when the data comes in late, but yeah, we try to keep the schedule. So by conclusion, that's only a summary. We provide these multi-gravity combinations from trace pressure on, and in the future, hopefully, also the new missions, augmented by the SLR C2 0, so you get complete information on the gravity field. And for this operational use, we have this fitted signal model, updated every 3 months. LEO PLB will clearly benefit from this model. GNSS will benefit in geophysical parameters like length of day. So please have it right. That's it. Oh, I have 23 seconds left. I'm fast.